There's a global race to build a useful quantum computer. These are machines that use quantum physics to solve certain problems much faster than otherwise possible. They're never going to replace your cell phone, but for things like material science or drug discovery, they could be revolutionary. We just published a paper in Nature, one of the world's leading scientific journals, called A Digitally Controlled Silicon Quantum Processing Unit. As a technical lead in quantum computing at HRL, I've been waiting for years to talk about this work. Qubits are the basic building block of a quantum computer. Their quantum properties typically emerge from being very small and very cold, oftentimes much colder than outer space. They also can't do anything on their own. Each operation has to be driven by precisely calibrated control signals. That means a full-sized machine faces two problems. First, how do you generate the millions of control signals that are necessary? And second, how do you deliver them all to the qubit without warming them up? Today, most labs solve this with brute force, racks of electronics and thousands of handcrafted cables. But that can only take you so far. Our qubits are each built with 3 individual electrons trapped inside of a silicon chip. We control them with voltage pulses that happen to be very similar to the digital logic of normal computers. That similarity was the key to solving both problems. It meant we could make a custom control chip that generates all the signals our 18-qubit devices need. It's manufactured in the same way as a normal computer processor, but uses so little power it can be inside the fridge right next to the qubits. It's cold enough that its connections to the qubits can be made with superconducting wires. These wires carry the signals almost perfectly, but not the heat, keeping the qubits cold. The other half of the story is our new qubit chip, which has dramatically lower device noise and is much more manufacturable than ever before. Put it all together and we get record-breaking fidelities for this kind of qubit and hundreds of rounds of error correction, all orchestrated by the control chip without any help from room temperature.
Everything you just saw, from the qubit chip, the control electronics, and the wiring, has been produced with silicon foundry techniques instead of expensive, hand-processed wiring and racks of custom electronics. When we think about quantum technology at scale, it's not just about the qubit chip. You also have to think about how are you going to control and wire it as well. Without answers to all of those questions, you're just doing basic research still, not product development. That's the promise of silicon spin qubits. Quantum computers that you can actually build at scale, and a cost per calculation that makes sense for real customers. The result that you've read about in this recent paper took hundreds of people many years to accomplish. No one knows who's going to win this race, but personally, I think the winners are going to use silicon to cross the finish line.